gives the keto form, and the protonation on O2 gives an enol form? Okay. They meant the oxygen. I don't know if they had a proofreader who just got excited and was like, oh, I know that oxygen is diatomic. O2 means oxygen. They must have forgotten that. I just did that and nobody caught it or what, but that's wrong. Okay.
So it should say protonation of the enol
On the O.
anion on the alpha carbon gives
Oh, yeah.
the enol form. So just cross out that whole middle.
Wait, protonation of the enolate anion. No, if you protonate the alpha carbon, you're protonating this guy. Add another hydrogen to here. Yeah, we can undo this actually.
So instead of O2, that should just say O negative.
Yeah, that should just be O. It
Okay.
should just be the oxygen. I just saw that O2 and was like, did I do something wrong? Why do we have oxygen gas? Oh no, you guys are just typing things. Okay. Because we're about to hit some reduction in oxidation, in which case we actually have all sorts of oxygens. Yes.
Also, isn't that backwards? Because if you protonate the
Yes.
enolate anion, it
I
would
did
be
draw it backwards. So,
no, the slide.
oh, the slide? Yeah.
If you
Well,
protonate the enolate anion,
and then this one is the enolate. So protonation of the enolate anion is going to result in either the enol or the ketone, right? It depends on where we protonate it. So protonation at the alpha carbon means we're going to put the hydrogen back here. And if we do that, if we protonate this guy takes a hydrogen, then we do go back to this. We go back to the keto form. And then if we protonate this, it goes there. But yeah, see, that's why sometimes the words in like slides are less helpful than just the pictures. Like I want them to be there because some people need to read it in words and then it's like, oh, okay, now it makes sense. But it is not the thing that makes the most sense to me. Pictures mean chemistry to me, and the words I have to translate to the pictures. Okay, so that was, sorry. There's something going on that my hair is just getting caught on. I think it's like a tag or something. And I can't handle it. Okay. Let's do the same thing with an acid. Because we can do that. I'm gonna write that after I finish this thing. Okay. So, literally the exact same thing except in an acidic environment. So we're gonna take that. You can call this, like it is a ketone, but also when referencing keto-enol tautomerization, you can call this the keto form, if you want. I don't know. I also think the keto diet has something to do with making somewhere in your body a ketone gets made, and I don't know, that has something to do with the keto diet. I don't know anything else, except that I think it was originally, I think it was originally come up with to help people with epilepsy or something like that. It was one of those like really specific things. Okay.
Children with epilepsy.
Yeah, children with epilepsy, right? Okay. Because like, I don't know, I just get very suspicious when, I get suspicious about fad diets, but that's just me. And I mean, I know that, like I know some friends who have done the keto diet and they're like, you know what? I don't know, it works for me and it made my weight a weight that I like, so all right, who cares? Like, it might be psychosomatic, it might not be, but whatever, it works for me. But I also don't, it's so much effort into what you're eating. I already have to work for food.
You don't
Like-
look like you have that much trouble keeping the weight off.
I have trouble eating. I have to go get the food or make the food, and it's terrible, and I don't want to. So I have a monthly giant shipment of carnation that comes to my house. Don't have to print that. But like, yeah, so. But I was also brought up, I know it's like a weird thing that I'm like, I hate diets like with a passion, and I don't want like unhealthy dieting, like I hate that that's a thing, but like, my mom grew up with weight issues because her mom was always talking about being on a diet. And so my mom was very specific to never say she was on a diet. She was always eating healthy if she was trying to like, but like she was never on a diet. And so I learned diets are bad. So anyway, it's a thing. But yeah, I don't know. I'm always suspicious when like something that's like, oh, this has like this use becomes like a health thing. Like I know there are a bunch of people with sensitivities to gluten, and so I know eating gluten-free became like it's a thing for some people with sensitivities to gluten. But for a little while, it was totally like a diet, like to lose weight. And I could be wrong, but I'm pretty sure they were still eating carbohydrates, just not gluten-derived, which doesn't really help you if you're not celiac or otherwise sensitive to gluten. But I mean, I don't know. Anyway, keto. I'm connecting this class to the real world, right? Sort of. This is, I don't know. Last year I talked about Elizabeth Holmes a lot. I don't remember how it came up, but ethics came up. And so we talked about Elizabeth Holmes, and she was just about to or had just started going on trial for all that stuff.
Yeah.
And
Was
also,
it when the documentary came out?
yeah, it was like right when the show and the documentary came out, and I had just started, my boyfriend and I went to a conference right before I started teaching, and we binged the show, and then binged the documentary, and then I started listening to the podcast right after, so I told everybody about it. And, ethics in science are very important. And it's okay to not be an expert in something, or to be an expert in something and not another thing. It's okay to not know things, because it's more important that, we consult experts and we just make sure everything's right. It doesn't have to be one person who knows everything. Just bring in all the people who know things. Listen to the people who know that weirdly niche area, to an alarming degree. Bring those people in, and then believe them, because, I don't know, engineers aren't chemists, and they shouldn't be expected to be, but they also shouldn't claim to be. Ethics is important, guys. The end. I went on a much longer spiel at that, I went on such a long spiel last year with that I'm pretty sure I put that as a quiz question. And those are open internet, so it was easy to Google if you actually hadn't listened in class or whatever, because it's not actually information you're expected to know. But all right, so acid catalyzed. First step we're gonna do is we're gonna go, hey, how about I put my lone pairs to good use? And oh wait, I want to go that way. Hydrogen. Why am I writing at the top of this board when I can't reach it? I don't know. Okay. We're gonna protonate the oxygen. I don't know why I'm doing this. I could do this lower, but I don't know. I just hate myself, I guess.
You're committed now.
Yeah, I know, I am. Hopefully, when we do a layer below this, it'll be fine. Okay. Oh, okay. When you see this specific mechanism, when you see it on the slides, there's going to be they have this step written out, and then they have mechanism arrows over here, and those mechanism arrows are just to undo it. So I guess they just wrote the mechanism to go forward and backward. And I don't like that because I don't want to redraw this thing. I just want to continue the mechanism. But don't get thrown off like that, by that like I did. All right, now we've got a deprotonated acid, which is conjugate base. So thank you for participating with me, guys. Like, for real. I don't know if it's actually helpful, but I don't know. I like it. It makes it feel interactive. So this guy can now deprotonate that, which is a pretty acidic hydrogen. And instead of drawing our arrows in one way and then doing resonance, I'm just going to draw them this way, and we will know that, yes, it resonates, and that's why it's more stable, but we're just drawing it the way that it... Yeah. Oh, no, not that, sorry. Okay, yeah. O, H, and two hydrogens left. So the enolate ion is not necessarily an anion, right? This is an enolate, and wait, do I count as an enolate? Honestly, no, I don't think so. Yeah, no, this guy is not an enolate. So I guess if you do acid catalyzed, technically you don't actually go through the enolate ion because it's an anion, but whatever. Base, acid, keto, enol, tautomerization. And this is the back and forth, so it's really easy to deprotonate these alpha hydrogens. And the reason we call this tautomerization is a rearrangement, right? So we don't call this a reaction because we lose a hydrogen, but then we gain a hydrogen. I didn't keep it green because, like, in reality, we're probably not gaining the same hydrogen. There's probably, like, a bunch of water, an aqueous base, or whatever. Like, there's probably a bunch of stuff in here, and the protons can all exchange whatever, and they're going all over the place, here and there. Especially since in this case, it gets protonated before you lose this, so, like, it doesn't have to be the same hydrogen, but it still cancels out like a catalyst, right? So we regenerate HA at the end, we regenerate B minus at the end. So that's a catalyst, and we've only done we've done a rearrangement, not a reaction, just because it has the same number of everything, yes.
So in a bigger, like, reaction, that would be like an intermediate?
These guys are intermediates. This tautomerization is, I mean, maybe I shouldn't have said it's not a reaction. I don't know. It's just usually when we do like a reaction, like we add or subtract. You know, we do like, I know it's not an addition reaction, and it's not an elimination reaction. And it's not really a substitution because we're not substituting one thing with another. So I guess it is a reaction. It's just, it's not those. We're not taking something away. We're not giving it something. We're not substituting one thing with another thing. We're just taking something from one place and putting it or its equivalent over somewhere else. So, yeah, it's a reaction. It's just a tautomerization. That's how we describe this rather than addition, elimination, substitution. Yeah? Okay, cool. Let's see. You know total 40? So, there's going to be 2 worksheets, and there might be an option of 2 worksheets in recitation today. Or at least I'm going to put one online that I made last night, but when I sent it to your TA to print along with the quiz, I sent him the wrong file. So I sent him a file that has like 2 questions on it, and then a key.
Let's do that one.
Yeah. I mean, you can, I'll post it online so you guys can work on it. He's got the key to it, so you can work on those questions or the other questions if you want, whatever. But, yeah. Okay, position of equilibrium. If there's at least 1 alpha hydrogen on a ketone or an enol, then they're pretty much going to be in equilibrium with their enol forms. Position of the equilibrium for simple aldehydes ketone lives far on the side of the keto form. I thought for a second, I could have sworn while I was reading, like ahead, while I was reading out loud, I saw left and I was like, shit, I'm trying to figure out which way, and then it didn't say left. On the side of the keto form. So basically, ketones and aldehydes, we're not lying to you. Usually they look like ketones and aldehydes. It's not like usually they look like this, and we've just been talking about this the whole time. But sometimes the equilibrium lies to the enol side. And I love how they're defining conjugation for us as if we haven't done a ton of conjugation already. So, for some molecules, the enol is the major form, or the only form present at equilibrium. For this form, well, for both of these forms, these alpha hydrogens, they're alpha to 2 different carbonyls, right? Like there's 2 carbonyls, but no matter which one you count from, this carbon is alpha from either of them. So I bet if you look on your pKa table, we've got, I bet there's an example of something like this, and I bet there's a different pKa for that. I could be wrong, but I suspect it's different enough to have to merit a value on there.
So those hydrogens would be more acidic.
Yeah, so these guys are going to be more acidic just because they've got, like, if you deprotonate this, you can resonate it this way and resonate it this way. So it's far more stable. Here too, you can resonate it both ways. So it's more stable than, while it's an anion, or while it's an ion, you can resonate it both ways, so it's more stable in between them. The reason that the equilibrium lies on this side for here is nature loves 6-membered rings, right? 5 and 6-membered rings. Nature loves them, like so much. Loves those things. So this oxygen, well, oxygen can hang out with hydrogen bonds, and this, well, that's the exact type of hydrogen that we need for a hydrogen bond because it's bonded to an electronegative oxygen, right? So basically, we make sort of a 6-membered ring. And if it existed exactly how we show it here, with one of them being a bond and one of them being just sort of a hydrogen bond, that interaction, then this distance would be longer than this distance, right? Because actual bonding is much closer than like intermolecular forces, right? Like intermolecular forces are between molecules. Hydrogen bonding is generally a type of intermolecular force, so like hydrogen bonding is strong and close together, but not as strong or close together as an actual like covalent bond, right? But because we've got all this resonance, and because this can resonate either way, you can protonate either this one or this one. So I'm not 100% sure if you can just resonate around in a circle and swap so that this guy now has the real bond and this guy is the hydrogen bond, but I would bet money that if you could get a crystal structure of this, that hydrogen would be equidistant between those. Because I think you could do that. Yes?
If you had a ketone with like an ethyl group on one side and a methyl on the other, which alpha hydrogen would be like technically more acidic? And like favored for polymerization?
Ooh, actually, that's what this guy is about. So that's a really good question. So here we've got, at least this guy is just a methyl, this guy is a CH2. In this case, we've got a CH2 and a CH and stuff. Do you guys remember which, if I'm gonna make an ion, if I'm gonna make an anion, is it gonna be more stable if I have CH3 negative, or if I have, like if I have a carbon with 3 hydrogens and a negative charge, or if I have a carbon with 3 methyl groups and a negative charge? Which one's more stable?
3 methyl.
Right. So, which side, wait, right, left, okay. For A, which side do you think the anion is going, which side of carbon side do you think is going to have a higher partial negative charge or more partial negative charge, right? Because it can go both ways, like we can do 3 resonance structures here, but which one on this one do you think is gonna have more negative characteristic? Obviously, the oxygen likes that, the negative charge most, but which of these, right or, yeah, this is right? Yeah, right or left? Raise your hand for left. Raise your hand for right. Yeah, that one stabilizes more, right? Major enol. And you know, I even think double bonds are more stable the more substituted they are. I want to say that was like, does anybody remember that from first semester? Okay. I'm pretty sure for the same reason double bonds are more stable. Yeah, okay, yeah. It says it right behind me, in front of me, because I'm facing this and not you. It's fine. So, in this case, right or left? Which side are we going to have the double bond on? On the right side or on the left side? Yeah! Yeah, there we go. Major enol, this one over on this side, because double bonds, I forget, like I think in terms of ion stability, because, I don't know, I think like you need to stabilize ions, they need some help. And double bonds, I mean, you can easily have double bonds on the end with like 2 hydrogens on the carbon, so you can like isolate this. This isn't just, I don't know, transit. I mean, not this one specifically, because not that one specifically probably. You can probably do that, but you might, if you tried really hard, you might be able to get some of this separated too. Anyway, yeah? Okay, does this make sense? Cool. Yes, we got through all of alpha carbonyl chemistry. So when we hit chapter 19, we're gonna come back to this and do a whole lot more alpha carbonyl chemistry, but yeah. All right. Yeah, class is long since over. Sorry. So, I did, however, send your quizzes properly, so he should be able to print out your quizzes. I sent him the wrong worksheet, so he's going to print out his worksheet and bring it. That's what you guys are going to turn in for your, like, attendance, participation, points, whatever. But also, I mean, it's attendance participation points. So you can work on that, and or you can work on the other worksheet that I made, which I am about to put on Canvas. And you know what? I'm just gonna put the worksheet and the key on Canvas, because I mean, who cares, right? That's more useful anyway. As long as I can bump them.